Speaker is Thomas Campbell from Canopy Biosciences. The talk title is ChipCytometry, High-plex Proteomics with True Single-Cell Resolution.
Yeah, thanks so much for the introduction, and a lot of great talks today, so I'm glad to be a part of this. As she just said, I'm going to talk today about ChipCytometry, which is a high-plex proteomics platform that's useful for spatial immunology. It's a platform it's an image-based platform that utilizes standard primary fluorescently labeled antibodies. And what's nice about it is that it's flexible in the sense that we can interrogate multiple different sample types, including cell suspensions like PDMCs, but also tissue samples, and retain that spatial morphology. And, the tissue applications is what I'm going to primarily focus on today, sprinkling in a little bit of information about the cell suspension applications as well. But before I kind of dive into the details of the technology, I just kind of want to take a step back and think about what cytometry is at its core. Of course, this isn't news to anyone on this call, but it's good to think about kind of what cytometry is at its basic, and where the challenges are kind of in the main steps of this. So, you know, the first step in any cytometric measurement is to identify each cell and separate all the cells from one another in a given sample. And then the second step would be to measure the biomarker expression of all the targets within that sample. And so when we look at these two steps, you know, in the first step, there are a few options in the context of looking at tissue samples. And the first one would be to degrade your tissues, which obviously when we do this, we're going to lose all of the important spatial information, which I think is sort of the next frontier for these, spatial immunology in tissues. And so then the second option would be to, of course, section tissues, where we take a very three-dimensional arrangement of cells and try to approximate it with a two-dimensional view. And when we do this, we have a lot of serological effects that result in spatial spillover from slightly overlapping cells in the third dimension. And so we try to address this with some various software applications, and I'll talk kind of about how ChipCytometry addresses this as well. And then moving on to the second step, of course, one of the main challenges here is covering the complete range of biomarker expressions we see in biology. This is particularly challenging for an image-based platform. We have to have a dynamic range of the image that captures the full true range of expression values we see in biomarkers in biology. And then the second main challenge, which we've been talking a lot about today, is just separating the signal of each individual biomarker in the assay from one another. So there are a few kind of approaches here, which we've talked about in detail today, looking at this in parallel. There's obviously some limits eventually that you run into in terms of multiplexing. So you could look at the individual biomarkers serially, which has issues in terms of throughput and really slows things down to an impractical rate. And so then the third option is the approach that we take with ChipCytometry, which is a combination of parallel measurements and done serially. So we do 5-plex assays in serial on the same sample. So the way ChipCytometry works, kind of looking at a 30,000-foot view, as I said, it's an image-based platform. So you stain the sample with antibodies. The instrument takes a series of images and draws a border around every individual cell in the sample, and then measures the fluorescence intensity within those defined borders. And from that, it generates a quantitative data set of those fluorescence intensity values for every individual cell. Looking at each individual marker in the assay, it produces a data set we're all very familiar with, similar to what we see in flow cytometry. And from there, you can do your index sorting and phenotype and subphenotype all the populations that you might be interested in a particular assay. The crux of the technology is really the sample chip. That's why we call it ChipCytometry. The samples are loaded onto little microfluidic devices that allow us to deliver reagents to the samples, and we can stain the sample with a cocktail of up to 5 antibodies, take a series of images, and then photo bleach away the fluorescence intensity from that stain, and then stain again with another cocktail of up to 5 antibodies, and do this iteratively, virtually unlimited number of times. And then the computer does some really complex image analysis, overlays all those images, image processing, and downstream data analysis of the data outputs. So to kind of talk about the different chips that we have, they come in a couple of different varieties depending on the applications. The photograph in the top left shows a rack of 4 chips. You can see that the reagents are delivered through a sample inlet just by micropipette. And you can see hopefully on your screen, you can see kind of this clear window. That's the microfluidic channel where the sample resides and through which the scanning and imaging is done. The inside of the channel itself undergoes a proprietary surface modification that, in the context of fluid samples like PBMCs, it's selective for viable cells because the cells adhere by electrostatic interaction, and then once they're fixed, their position remains constant throughout the cycling from one cycle to the next. The kind of third variety over here of the chip is the chip that we would use for tissue applications, which is different from the other two in the sense that there is no real sort of bottom wall to this microfluidic channel. Instead, the tissue is sectioned and fixated to a cover slip. And then on the back of the chip, there's just an adhesive. You peel off a piece of paper, just like a sticker, and then press that down onto the cover slip. And so the cover slip sort of forms that bottom wall to the microfluidic channel. One of the most incredible applications that falls out of this chip technology is the ability to store and preserve your sample. So ChipCytometry is a non-destructive analysis process. So the samples remain after you do your initial analysis. And we validated that samples are preserved and the epitope stability of your targets is preserved on the chips for up to 2 years when stored in a refrigerator. So there's a couple of really nice applications that fall out of this. One is we know that the process of freezing and thawing PBMCs, which is a process that's used a lot in the clinic, sort of eliminates or sort of introduces what we call the cryobias, where this freeze-thaw cycle it interrupts the epitope stability. And so by eliminating that need to freeze-thaw samples and storing them on the chips, we can eliminate that cryobias. But also another application is the ability to reinterrogate samples and add additional markers to your assay after that initial analysis. So you can look at 10 or 15 markers right when the samples are collected. You can put the samples in the fridge. You can begin to analyze your results. If you're looking at a clinical trial, you can begin to collect more and more results and add samples to your analysis. And in some number of months or maybe a year or two down the road, you can add additional markers to your assay anytime. And in that, those additional data points just go on top of the original data set. And so here's sort of the endpoint. We're able to image tissues and phenotype every single individual cell on the sample. Individually, we have a quantitative expression level for each marker in the assay for every individual sample, or every individual cell in the sample, and we know its spatial orientation in the tissue. One thing that's quite unique about ChipCytometry compared to some of the other image-based or multiplex proteomics platforms that are out there is that we don't use any proprietary antibody conjugations. So we use just regular commercially available antibodies, primary antibodies conjugated to fluorescently labeled dyes, or fluorescent dyes. And this is really nice in that you aren't really limited to whatever a particular manufacturer has commercially available. As part of our service business, we've validated more than 250 commercially available clones on the ChipCytometry platform. Here's just a list of the markers we have validated for human PBMCs. We have other panels for human and mouse and non-human primate PBMCs and tissues. So I kind of want to talk about some of the key features that help us address some of those challenges in cytometry and image-based cytometry that I introduced at the beginning of the talk. The first is resolution. I think with any image-based platform, resolution is something that's obviously important, and I think it's also fairly easy for us to wrap our minds around this. We're used to thinking about resolution even just with our personal devices and TVs and things, but obviously the higher the resolution, the more single cell and subcellular information we're able to extract from a cytometry process. And these images here kind of represent the range of resolutions that you see on the market for image-based cytometry platforms. The second one, which might be a little bit more less familiar to some people, is the concept of dynamic range. And in the context of an image-based platform, dynamic range is really the main driver of your signal-to-noise capabilities. And so with ChipCytometry, we use a high dynamic range camera, which is actually not a trivial thing to do in a quantitative scientific process. So these two images here demonstrate the image quality from a high dynamic range image on the left collected with the ChipCytometry platform, and then a lower dynamic range image that's representative of some of the other platforms on the market. And you can already kind of see just the amount of information that's lost when you look at this lower dynamic range image compared to the higher dynamic range image. But it's not something we can actually accurately kind of compare with our eyes, because our eyes aren't capable of discerning a full 8 logs of dynamic range, and also the displays we're looking at aren't capable of displaying a full 8 logs of dynamic range. So another way to look at this is, of course, with a dot plot. And when you look at a dot plot, you can really see the importance of a high dynamic range measurement in the context of biology and cytometry. We see in this plot here showing the protein expression levels of interferon gamma, we see an expression range that's about 6 logs. So of course, if we want to make this measurement quantitatively, we have to have a detector or a camera that has a dynamic range that's greater than 8 logs to do this quantitatively. And then kind of the downstream implications of that, of course, if you compare these dot plots here, on the left is a dot plot comparing CD8 to CD3 to identify the cytotoxic CD8 T cells. You can see that, the dynamic range on this particular dot plot is upwards of 4 logs. And compared to a dot plot on the right from a sort of competing platform with much lower dynamic range, you basically lose the ability to identify this particular cell population, which may be very important for your analysis. Another area where dynamic range is important for an image-based platform is the concept of net fluorescence. And obviously with tissues, we have some baseline autofluorescence in background. And what we do with ChipCytometry is we take a pre-stain background fluorescence image before every single stain cycle, and then we subtract that from the post-stain fluorescence intensity, and the fluorescence intensity values are calculated based off those net intensities. And if we want to do this process in a quantitative manner, it's really critical that both the pre-stain fluorescence and the post-stain fluorescence intensity lie within the linear dynamic range of this detector, in this case of the camera. So just to kind of summarize all this, the main challenge here is downstream of collecting the image is processing the image, and that involves drawing borders and segmenting each of the cells and then measuring the fluorescence intensity inside those borders. You can have the greatest, most powerful cell segmentation algorithm in the world, but if you are feeding poor or low resolution and low dynamic range images into that process, you can imagine it's making the algorithm work much harder, and sort of that's the limiting factor is the image quality input. And so that's really what we've optimized with ChipCytometry. You can sort of imagine if a computer were to try to segment this image down here compared to this image, it's going to have a much harder time, and the same looking at the resolution aspect. And so ChipCytometry involves every step of the process, from collecting the image sorry, from preparing the sample to staining the sample to collecting the image, and also the cell segmentation algorithm in downstream analysis. And unionizing all these components together is a really important feature of ChipCytometry as a platform. And sort of the gold standard for interrogating this process, I think, and how successful the imaging and cell segmentation of a platform would be definitely to look at a tissue like mouse spleen, which is a tissue that's very densely packed. The cells are small and densely packed, and so it's a challenging tissue to try to segment. And here we can compare the expression of CD3 and B220 on mouse spleen, which is your T cell and B cell marker. And of course, you can't be both a T cell and a B cell, so you wouldn't expect biologically to have any double positive cells. And we see here that on this top plot, we have just 0.75% of the cells are double positive, which means that only 0.75% of the cells are expressing both CD3 and B220. And if you're familiar with any image-based cytometry platform, this is really a staggering number, and it's the result of a really high-quality imaging platform that addresses those challenges with resolution and dynamic range that I mentioned, and also a really sophisticated cell segmentation algorithm. So moving on to some of the kind of key applications, of course, looking at the immuno-oncology applications. Here is looking at the T-cell infiltration in a human head and neck primary tumor. I like this image for a couple of reasons. You can kind of see the tumor heterogeneity. If I can orient you on kind of the bottom right corner here is the tumor edge, and you can see how the CD4 is differentially expressed compared to the FOXP3, which is more concentrated on the border here. And another thing that I like about it is you can really see this kind of subcellular resolution where you have CD4, which is a surface marker that's localized on the surface of the cell, while FOXP3 intracellular marker is localized intracellularly. And this is something that's really nice about an image-based platform, is you can sort of interrogate these things, the intracellular versus extracellular and subcellular resolution of the staining patterns. Here's an example of CD279 or PD1 on that same exact head and neck primary tumor. The reason I like this image here is because we are staining for both CD45 and PD1 on the same sample. This is a high expressing and a low expressing marker on the same image. And the reason we're able to do this and do it quantitatively is high dynamic range imaging, which I've mentioned before. And so we're able to quantify the expression of PD1, and you can see we've quantified there that about 12% of the T cells in this particular sample are expressing PD1. And then kind of downstream of that, this is something I'm sure you guys are probably familiar with these types of comparisons, but in this particular study, we were looking at the T cell infiltration or the immune composition of two tumor sites on the same patient, a primary tumor and a metastatic tumor. And using ChipCytometry, we were able to quantitatively phenotype all of the immune cells, the key immune populations in these two sites, and see some pretty big difference in the T cell composition and the T cell infiltration of the two sites. This next image here, I just like to show because all the images previously I've just showed a couple of markers on top of each other. This is a highly multiplex process where we can do many markers on top of each other with the serial staining. And within the image analysis software, you can toggle on and off each marker. And this is just showing a more high-plex overlay. This is a 13-plex assay on a human non-small cell lung cancer sample. Of course, as you start to pile on more markers, it gets a little bit harder to pull out meaningful information with the human eye, which is why in the previous slides I've just shown the lower plex. But within the software, you can just toggle on and off all of these markers individually and kind of show whatever combination you're interested in looking at. So to summarize, ChipCytometry is a platform that combines really high quality imaging and powerful analysis software to enable true single cell resolution. We can quantitatively measure the expression of every single marker in your assay for each individual cell and maintain that spatial information of how they're spatially arranged. With the chip technology, we are able to validate up to 2 years of sample stability, which eliminates the problem of cryobias for clinical samples. It allows you to save and reinterrogate precious samples as you need. It's flexible in the sense that it works with many different sample types, as I mentioned. And it's also a highly multiplex process. We validated over 120 biomarkers for PBMCs. This number continues to grow. And as I said, it's open source with regard to the antibodies and the conjugation chemistry we use, so there's no proprietary conjugation. You can access ChipCytometry a couple different ways. We sell the instruments themselves, and we also offer a clinical service offering. The instruments come in kind of 2 different varieties. There's a benchtop cell scanner one, which all of the scanning and imaging is fully automated, but some of the staining and the bench chemistry is a more manual process. So for that reason, it's a little bit more ideal for exploratory or early phase clinical trial applications. And then the Cytobot is a larger standalone, fully automated system. It has liquid handling that can do all the staining, completely automated, and can run 24/7. So for that reason, it's good for larger clinical trial applications. And what's nice about the way the system was designed is that the kind of base model Zell Scanner 1, the microscope that's used on that can be sort of plugged in to the Cytobot, so you can sort of scale up your throughput as the study progresses and the throughput needs increase. So I think I went a little bit under time, but that's okay. I've got plenty of time for questions. I'm happy to answer any questions you might have. And if we don't address anything, I have my contact information up here. I also left the contact information of Wendy Laird. She's the Director of Business Development for the New York, New Jersey area. I know at the start of the call, it looks like we have some people from all over the U.S. So if you have any questions or would like to talk to anyone, you can contact me and I can talk to the right person.
Wonderful. Thank you so much, Thomas, for the great talk. We really, really appreciate it. We definitely do have a couple of questions that popped through. So I'll start with the first question from Rohit. So he asked, or she asked, is it possible to image and count the number of synapses between T cells and tumor cells using the ChipCytometry?
I'm not familiar with if we have done that before. I think, if you have a good marker to look at this in some other assay, the nice thing about the way that the way this platform has been built is that it's really compatible with a lot of the other platforms that you're familiar with. We're not using any proprietary conjugation chemistry or anything like that, so that leads to some good capabilities in terms of cross-validating across platforms and things like that. So I'd be interested in learning a little bit more about specifically, what you're looking at there. But there's a good chance we would be able to do that.
Okay, wonderful, thank you. And certain parts of that cut out a little bit with the mic, so just to, in case there's a mic in a certain area by your laptop, just so you know. And then Rohit also had a follow-up. Could you please provide details on the camera specs?
Yeah, so it's a CCD camera. I showed the resolution there in the dynamic range. I think those are the most important specs, and I could give you a little bit more information kind of offline. I don't have the specs off the top of my head, but 500 nanometers resolution and 8 logs of dynamic range are kind of the most key specs from a image quality perspective.
Okay, great, thank you. Then we have a question from Yolanda, and she's asking, does the analysis software provide the ability to interrogate spatial parameters? For example, AV distance of CE type A to cell type B, relative frequency of interactions between cell types A and B, etc.
Sure. So within the software itself, we're still developing those particular analyses. The data outputs are regular TIFF files, which can be exported and imported into whatever image analysis pipeline you're used to using. And we've had a lot of customers do those sort of downstream analysis using other platforms.
Okay, great. Then Kevin had asked, what is the difference between ChipCytometry and histocytometry by Gerner et al. In 2012? And also as a follow-up, what type of tissues can be used?
So to the first point, I'm not 100% familiar with, I'm not familiar with that, that citation. I could look into that and get back to you on the specific differences. You know, there are a couple of other platforms that are out there that differ in sort of the way, I mean, there are all sorts of differences, but maybe the dye activation is one main way. And also I think the microfluidic chip is one kind of key proprietary aspect of this. And of course the cell segmentation algorithm. So I'm not familiar with the specifics of that paper. I'd love to get back to you with that. The second question was what types of tissues we have done. The system works on both fresh frozen and FFPE samples. We do, you know, a lot of mainly, you know, tonsil and all sorts of different human tumor types, and also like mouse PDX models and things like that. So in our CRO business, we've done all sorts of tissue samples, a wide range.
Perfect. Awesome. Well, I think that's, those are all the questions that we have for today, and it's pretty perfect on time. So Thomas, that was really wonderful again, and thank you so much for that wonderful presentation.
Thanks.